Today, I'm going to talk to you about a groundbreaking hypothesis regarding the rate at which the universe is expanding. Let's dive right in. The Earth, the solar system, the Milky Way, and a few thousand nearby galaxies are moving within a vast bubble that is 250 million light-years in diameter. The density of matter inside this bubble is half as high as the rest of the universe. This hypothesis was proposed by theoretical physicist Lucas Lombriser from the University of Geneva to address a decade-long debate in the scientific community. How fast is the universe expanding? Until now, at least two independent methods of calculation have arrived at values that differ by about 10%, and this discrepancy is statistically irreconcilable. However, this new approach, published in the journal Physics Letters B, resolves this discrepancy without invoking any new physics. The universe has been expanding since the Big Bang, which occurred 13.8 billion years ago. This idea was first proposed by Belgian physicist Georges Lemaitre and demonstrated by American astronomer Edwin Hubble in 1929. Hubble discovered that every galaxy is moving away from us and that the most distant galaxies are moving the fastest. This suggests that there was a time when all galaxies were in the same place, indicating the Big Bang. This research gave rise to the Hubble-Lemaître law, including the Hubble constant, h0, which denotes the universe's rate of expansion. Current best estimates for h0 suggest that the universe is expanding 70 kilometers per second faster for every 3.26 million light-years. However, there are two conflicting methods of calculation. The first method is based on the cosmic microwave background, the microwave radiation that comes from all directions, emitted when the universe was about 370,000 years old and cold enough for light to travel freely. Using precise data from the Planck space mission and assuming the universe is homogeneous and isotropic, a value of 67.4 is obtained for h0 using Einstein's theory of general relativity. The second method relies on supernovae, which occasionally appear in distant galaxies. These bright events provide highly precise distances and yield an h0 value of 74. Professor Lucas Lombriser from the University of Geneva explains that these two values have become more precise over the years while remaining different. This discrepancy sparked a scientific controversy and even raised the exciting possibility of new physics. To bridge the gap, Lombriser considered the idea that the universe might not be as homogeneous as previously thought. This hypothesis is more evident on relatively small scales, where matter distribution inside a galaxy differs from outside. However, imagining fluctuations in average matter density on volumes thousands of times larger than a galaxy is more challenging. If we were in a gigantic bubble, Lombriser continues, where the matter density was significantly lower than the known density of the universe, it would affect the distances of supernovae and ultimately the determination of h0. For this Hubble bubble to be large enough to include the reference galaxy for measuring distances, Lombriser established a diameter of 250 million light-years. He calculated that if the matter density inside was 50% lower than the rest of the universe, a new Hubble constant value could be obtained that matches the one derived from the cosmic microwave background. The probability of such a fluctuation on this scale is between 1 in 20 to 1 in 5, so it's not just a theorist's fantasy. There are many regions like ours in the vast universe, says Lombriser. So there you have it, an exciting new hypothesis about the rate at which the universe is expanding. If you enjoyed this and want more science and space news, don't forget to subscribe to our channel. See you in the next video. Goodbye.